Welcome back to Roll and Tutoring. If this is your first time joining us, be sure to hit the like button and subscribe as you are watching the video. If you would like to have your problem solved on the channel, please message us given one of the methods listed in the video description. Today we are looking at a fluid mechanics problem, and the problem statement is as follows. If the artificial atmosphere consists of 20% oxygen and 80% nitrogen by volume at 14.7 psia and 60 degrees Fahrenheit, A, what is the specific weight and partial pressure of the oxygen, and B, what is the specific weight of the mixture? So the first thing you'll need to do is you'll need to have a book to be able to look up, like we have here in the appendix. We will need to find our gas constant R for both our oxygen and nitrogen. So we'll go ahead and grab those numbers while we are here. We have the gas constant R of our nitrogen. I'll do that with an R sub n equals 1773, and that is in foot-pound per slug degree ranking. And then we have our R value of the O is 1554 with the same unit here. So once we have that, we can go ahead and start solving. So like I said, make sure you grab a book to find the R values that you need. We'll readjust here so you can better see. Alright, now that we have those, we will go ahead and pull from our equation list. Or if you do not have an equation list handy, so as we seem to have here we go. I was going to say as we seem to have misplaced ours, we're using one of the perfect gas equations, density, gravity, pressure, or constants that we just looked up, and the temperature. So we'll go ahead and use that. So we say for 100% oxygen, or O2, which is how oxygen typically forms, we will have our density equals, and for here, when you're not using SI terms, gravity is actually 32.2 times our pressure, 14.7 times 144, which is 12 squared. To get inches here, because it's pounds per square inch, just to remind you of that. And then we put that over R, which is 1554, times, now remember the problem statement gave us temperature in Fahrenheit, and as you can see by this, we need it to be in ranking. And we do this by adding 460 to our temperature. So we can go ahead and plug that into our handy dandy calculator here. 32.2 times 14.7 times 144 divided by 1554 times 460 plus 60. And be sure, if you're doing it straight in a row like this, you're making use of your parentheses or you'll end up with the wrong number. So here you should get a number of 0.0843. If we cancel out all of our units, we'll get pounds per foot cubed. And you should always, if you're getting density, it should be a pound per foot cubed when we're not using SI units. So once we have that, we'll have to do the same thing for our nitrogen of 100% N2 And that will equal nearly the same thing of 32.2 times 14.7 times 144 over, but now rather than using the oxygen one, which, sorry I didn't write that up here, we use the nitrogen one of 1773 times 460 plus 60, and we'll go ahead and type all of that in. And you should get 0.0739 pounds per foot cubed. Alright, now that we have those two things, we can start looking at question A, the specific weight and partial pressure of oxygen. So 1 foot cubed contains 0.2 foot cubed of O2 plus 0.8 foot cubed of N2. So for 20% oxygen, we would have our density of 0.2 times our 0.0843, which would give us 0.001686 pounds per foot cubed. You can round that to whatever significant digits you need to, but that is our first answer for our partial or the specific weight. And then we can find our partial pressure by using that same gas equation, only now we are going to switch it around, so we have P equals specific weight times R times T over gravity. So we're searching for our partial pressure, so we can go ahead and plug in this answer we just got for our specific weight, 0.001686 times, we'll still use the R that we originally found way back up here for O, our oxygen of 1554. And our temperature is the same. We'll be using 520, which is this 460 plus 60. All of that over our 32.2 for gravity. So now if we go ahead and plug all of those in, we get 442.3, which is actually going to be 423 pounds per foot cubed if you adjust for units. And that's absolute. And then if we go ahead, you can look through your book and find the conversion from pounds per foot cubed. So if we go through and find pressure, pounds per foot cubed to get to PSI, which is equal to 2.94. And those equations can just be found in your book. So you should have an equation page right at the beginning, something like this. So once we have that, that will be our second answer. Our first answer was right here. Now we can move on to problem B, which is the specific weight of the mixture. And we can do that by finding our nitrogen, because we already found the first part. We have our 20% here, right? So for our 80% nitrogen, we'll go with B here, we can do our specific weight equals 0.8 times the one we found way back up here of 0.0739, which will give us 8 times 0.0739, 0.0591 pounds per square foot. So the mixture then would have to be the combination of this number and this number. So we get our 0.01686 plus 0.0591. And again, you can round those however you see fit, but that will give us 0.07596 or 0.076 pounds per cubic foot. As your specific weight for the entire mixture. If you need more help on a fluid mechanics problem or other homework problems, please contact us to either have your problem solved on the channel or to inquire about tutoring, and our contact information is available on any of the methods listed in the video description. Thank you and have a great day.